Okay, thank you very much, Ove. Like everybody else, it's my name only here, but there really should be about 40 other people listed there, and we just don't have the space for it. So a lot of effort has gone into this. Let's go forwards. So the key question we're interested in is basically taking off from where Terry says, there's still time for action, it's not too late. And we basically wanted to do a risk assessment for the future. And risk assessment as to how we had to pick a parameter. So we picked net calcification rates for coral reef ecosystems and how they might change, arguing that positive net calcification rate is essential if a reef is to recover from impacts of cyclones. And likewise, from a human point of view, it's very important to coastal protection. I think NOAA estimates that the reef for Florida is worth 47,000 K per meter in terms of coastal protection. So the two scenarios we wanted to discuss were basically the business as usual scenario, where we don't do very much to reduce the rate of CO2 emissions. And the second one is where we put effort into it and see whether there's any real difference to motivate action in that area. When you put CO2 up into the atmosphere, you have two impacts on the ocean. You have very nice, Michael illustrated it, the impact on acidification, but you also get warming. And so we wanted to see how those impacts affected the reefs together. So just to justify the treatments we used and the idea between business as usual, where CO2 emissions keep climbing through till 2050, versus a scenario where they start to reduce through time, we selected these A1FI and the B1 scenarios and mapped the temperature anomalies predicted for each, and then also mapped onto them the temperature, the PCO2 changes. And you'll notice in the previous slide, I referred to these as plus values. So instead of exposing to 950 ppm of CO2, I said plus 570 to take us from the 380 value we have today. So the idea is, when you go and perform an experiment is, we're going to add temperature and heat, but what do we add it to? Do we add it to the medium temperature that the things are exposed to, or do we add it to a variable baseline? And so for us, we went to Heron Island, and we decided, and Heron Island is great because the temperature varies quite significantly through the annual period of time, about 7 degrees between winter and summer maxima. And likewise, the PCO2 varies between the periods of time. Interestingly, it's higher in summer than it is in winter, potentially because of metabolic stimulus. So the other nice thing about working with these types of variable baselines is we can acclimate our experiments. If we start at just after height of summer around March, it suddenly starts to cool off quite steeply. And so if we're using an A1FI scenario where we're sort of applying plus 4 degrees, okay, and we acclimate them slowly through time, we don't actually have to heat the treatment at all. We can just maintain the temperature through time, and therefore we give it a soft introduction to the treatments we're going to do over the long period. At Heron Island, the water intake is taken straight off the reef here. If you look where the water intake comes, there's not a coral in sight. It's basically a sediment bank. So we went offshore, and we went down to collect all of our organisms around 5 meters, where we could use blue filters to basically mimic the light environment on the coral deck at Heron Island. So the key goal we wanted was basically to derive net calcification budgets over an annual cycle. Okay, and how do you go about doing that? Well, the key thing we need to know is two things. is not only just what corals are doing, what live corals are doing, or what halimeda and how much calcium carbonate they're laying down, we also need to know the rate of mortality of corals in the different treatments, and also some idea of how fast they're going to get bioeroded. Corals that are dead tend to bioerode faster. And so the efforts to answer this question, and the ones I'm going to talk about today, we've split it into looking at the net calcification rates of reconstituted patch reefs from Harry's Bommy. Okay. We've also looked at calcification rates of a variety of hard corals. As the previous talk mentioned, you get variable responses. And we also want to know what the response is in winter, which in our case are warm, but not excessively warm warm temperatures under an A1FI or business as usual scenario, versus the summer, where we definitely breach the long-term temperature maxima, as well as having the acidification going with it. So we calculate mortality rates, and secondly, we want to know what dead corals are doing. You know, how much of that substrate, how quickly can it disappear over time? And we focused on some of the roles of bioeroding sponges and the endolithic communities. And I think the key message to remember is that a reef that grows slower still has an ability to recover from cyclones, but one that has stopped growing altogether has zero ability. And so if that's what differentiates doing something and doing nothing, it's a big motivator for doing something. So our patch reefs look like this. This was the first experiment that we've recently published in PNAS, and we put in a whole collection of organisms to try and replicate what was out in the reef. Our percent cover of coral is about 35%. We put in algae, but because this is a flow-through system, we also get algae that are constantly being introduced into the tanks through time. And we tried to put in some herbivores and some digitivores to try and keep the system healthy. So the first experiment turned out to be an experiment about what happens over the summer period. Okay? And so we went from early November through till early February. And the black line is the temperature that actually we're trying to follow at Harry's Bommy through time. The green is a pre-industrial where we reduce the temperature by 1 degree and the PCO2 by 100 ppm. And as you can see, we actually follow the trends at the different levels fairly well in our system. I've reported here, we measure the pH in the tanks. We control the CO2, but measure the pH. And you can see that the average pH on A1FI is 7.7. It's not excessive. It's not 7.4 or 7.1. But the basic thing that we saw happened for this period of time, we used alkalinity anomaly method for assessing calcification rates, and we did them over 3 time points. Okay, across the treatment. And we came out with an average. And this was the big finding, that these tanks were actually decalcifying, okay? Whereas under reduced rates of CO2 emission, they're still gaining calcium carbonate, albeit a bit slower. When we broke that down and we wanted to know what was happening by day and by night in the system, so our measurements on the previous slide are based on 4 measurements taken over the course of 3 days, day, night, day, night, day, night. What we saw was that we actually increased decalcification by night quite substantially. And so the threat was occurring by night, a little bit of decrease by day, but mostly by night. Okay. So when we looked back at our tanks and we looked at what were the main components of calcium carbonate in our tanks, well, they were coral, and then there was sediment, which we had about 3 centimeters of sediment in the bottom of these tanks. And when we looked at the difference between the B1 or the reduced and the business as usual components, both of them were reduced, but they didn't differentiate B1 versus A1FI for our summer experiment. Okay? But when we looked at the sediments, we actually found that the sediments were much finer, okay, under A1Fi, that there appeared to be dissolution amongst the sediments. And when we further tried to explore what was driving that, we took some microbial samples for the pore water around the sediments to Gene Tyson at UQ, and he did an analysis for us. And we found that, surprisingly, the community composition of the microbes didn't change. But what happened under the business as usual was the microbial populations, their abundance went through the roof. And so what we think is happening, and I think this comes back to Terry's question, is that the microbes, there's much more CO2 production in the local pore water environment, and that is actually able to undersaturate the local environment. Okay, and that's why we get such significant dissolution. So that was the end of the February experiment. We terminated it there. And when we looked, this is the strip for the different treatments in February when we came to the end of that experiment. And this was the pre-industrial where we had growth. The year we had applied the data, the treatments to, the baseline got fairly hot in January, and it led to bleaching just after in February, even in the controls. But in the other tanks, we had bleached corals, and we had some mortality in the background. But we really want to know what's going to be the impact of an annual cycle. So we started the experiment again. Okay, we kick-started we filled the tanks in March, we kick-started in April acclimation, and we reached the treatments by August. So what I'm going to show you now is a monthly trip through the different events. So this is the control. Okay, so every click is a month that goes past, and so it's going from August all the way through to July. And what you can see at the end here is, you know, we got really nice growth. We're not bad at keeping corals in these tanks. We do quite well. This particularly grew phenomenally, and in some cases we started off with plate corals that were this size, and they broke in, and they ended up being 3-tiered and this size in the pre-industrial. So we saw quite substantial growth under these treatments. However, when we went to, this is the B1 scenario, okay, what we saw is, please focus on this platygyrid up here, and halfway through you'll see it go bone white, and then you should see it there. In a month, it picks back its pigmentation quite significantly. So we saw the bleaching go through. A lot of the corals died, okay, the usual more susceptible plating corals, the Seriatoperas, the Postloperas, and the Acroperas didn't make it through. But we got Lobophilia, the Parietes actually pick up and make it through, and Fungia also, over here, does really well. So these corals are bleached almost for 4 months, and then they're still able to bounce back and come back under this treatment. However, when we moved into the do little to reduce CO2, okay, the impact that we saw is quite different. So as we go through February, March, and then we hit April. And you'll notice that is just a slimy cyanobacterial tank with everything in the end dead. Okay, towards the end here, okay, by July, we've got Caulerpa and other things coming to grow in the tanks, but there's no coral significantly alive. So when we looked at the net annual response, we do start to see some changes with regards to the coral communities that perhaps we didn't see so clearly when we just looked at the summer response. So under B1, we get bleaching and recovery, whereas under the A1Fi, it's just bleaching and death. Okay, and we're currently looking at all the numbers and all the other experiments. The experiment's still running. We're a year and a half. We're going to terminate it in February, and we want to know if what these recovered corals do through the subsequent summer. So the next topic is to look at the hard corals in more detail. And so we've been working with these 3 different corals. This guy appears to be able to survive under the B1, whereas these guys don't seem to be able to make it through the summer at all. And we just wanted more details, so we went to tank experiments using nubbins to see what happens to them through time. So this is quite, I tried to squeeze everything on one slide, I probably shouldn't have. But this is the, here summer is referred to the early summer response. It's November, December. We haven't got to that height of temperature in January and February in these experiments. But what I wanted to focus on to start off with is to look at the brain coral, the platyjarid over here. We're currently doing the summer experiment for this coral to see how it weathers through the summer. But clearly, we got no mortality through winter under any of the treatments in this case. We got almost no change through all of these different treatments. But under A1FI, despite the fact it's warmer, the more acidification, no growth whatsoever. So we get a very substantial difference between these two treatments. When we come to the acroporas, okay, down the bottom here, I've just put the mortality data for the acropora. One thing we were quite surprised is that across the board in winter, acropora at Heron Island, when we bring it into our tanks, doesn't survive as well. So roughly 20% of the branches we put into whatever treatment die, whereas when we work in the summer, they are much more robust, at least in the control and the cooler temperatures and conditions. But when we got to the A1FI, you know, even before we've hit the height of summer, we're seeing high mortality. And that sort of mimics what we see in our mesocosm treatments. When it comes to calcification rates of live corals, okay, we see significant reductions across in the B1 and A1FI compared to summer rates, okay, but they're not that significantly different. But what we did is we also threw dead branches of coral in at the beginning. We allowed them to get covered with epilithic algae, and we also measured their decalcification rates. And this is where we saw a really big impact. A dead branch that's covered with epilithic algae under A1FI decalcifies very, very quickly. And so what we argue is you put the mortality together with the lack of growth in the winter, and you really do get a significantly worse effect under A1FI than you do for B1. Stylophora pistillata, we saw some examples of that in the last talk. There are many morphs of Stylophora pistillata, maybe many different species of Stylophora pistillata at Heron Island. Okay, so we worked with a brown morph. It has either a C35 or a C78 clade of symbiont in it, versus the pink morph that has the C8A clade of symbiont in it. What was interesting with this Stylophora is it showed that it actually did like the winter, hotter, more acidic scenarios. That's when it really grows really well. We got different performances in the summer with respect to the different morphs. But the clear thing that however well it grew in the winter, it just can't get through the summer in either of these treatments. So its resilience to the winter conditions and to the acidification levels in winter, okay, just potentially might mean very little compared to the high mortality rates we get in the summer. So just to move on, finally, to talk a little bit about the Biceroding response. Here I'm talking about the work of one of my graduate students, James Fang, who's just finished up and disappeared off to Norway for a postdoc. He worked on Cleona orientalis, which is a bioroding symbiotic sponge. Like corals, it has dinoflagellates in it. And he monitored the rates of bioerosion on coral skeleton, in this case, Parietes skeleton. And then also, Catalina Reyes-Nivia, she's just finished her PhD, and she was looking at the effect of endolithic algae on both coral dissolution and on CCA dissolution. So James's responses, I just wanted to quickly characterize them. Okay, his experiment ran in the early part of the summer from October through to December, And these aren't calcification, these are dissolution rates here. And you can see the dissolution rate significantly increasing as we go from different treatments. So not only do corals grow slower, die more frequently, but that actually the erosion rates would appear to be increasing. Up here, you've got the look of what happens to those sponges through time in the experiment. And you can see that under the A1FI, the sponges lost quite a number of their dinoflagellates. Okay? And these dinoflagellates are meant to be mutualistic and support the growth of corals. So we had two different responses. We had bleaching, but we had also huge amounts of bioerosion going on. This is an integrated response. It was measured using buoyant weight changes. So it measures the response over from October all the way to December. Okay? And when we looked at the biomass of these sponges and how it had changed through time, what we found is the biomass change was greatest in this treatment, followed by this treatment. So we did some carbon budgeting. We measured photosynthetic respiration rates. We also accounted for heterotrophy and the loss of carbon eliminated from the system to monitor how much, at the end of the experiment, carbon would be available for the growth of the animal, in this case, the sponge. Okay, and what we found by A1FI in December is actually negative. Okay, so this is the one case where I would say this hike in A1FI bioerosion might be significantly different if we viewed it late summer and we did an annual budget on it to see how it's going to change. So we still got a substantial amount of work to do there. However, likewise, we looked at the Endolithic communities, and this is Catalina's work, Reyes Nivia. The endoliths are made up of photosynthetic microalgae and also fungi and heterotrophs. And so she looked at what happens in the corals, and this is a rate of dissolution in light-dark cycles, and other places where she just put them in the dark so the photosynthetic organisms had died off and disappeared. And what you can see here is that actually in the light for the corals, we also got that increase in decalcification occurring. With the coralline algae, we get different light-dark patterns, but you also see that increase in decalcification pattern occurring. And I think this is very important when we're looking at what's happening with decalcification, especially in local environments, is that what's happening with respiration and CO2 production at night, what might, from the water column point of view, be an impossible, not give you states of undersaturated water for carbonate. If you add and value add the CO2 that is produced by the respiring microorganisms or respiring heterotrophs or what happens through the night, you can actually significantly drive down the pH close to where the skeleton is located and actually get to undersaturation through the biological activity of the organism present. So with that, I'd like to just finish up. My key question was this: is there a difference? And I think the answer is most positively yes, there is a big difference. There's a big reason to go to action and to reduce CO2 emission levels. And I'd like to thank all the members of the CRE lab, Gene Tyson and his lab that helped us with the molecular analysis of the microbes, and also all the funding agencies that have helped us build the system at Heron Island. Thank you.